Hello and welcome. Today, we're exploring a fascinating consequence of Albert Einstein's special theory of relativity that was, for over 6 decades, just a thought experiment. It's called the Tyrrell-Penrose effect, and it describes how objects moving near the speed of light would visually appear rotated, not just contracted. You might know that special relativity predicts length contraction for objects moving incredibly fast. However, in 1959, James Tyrrell and Roger Penrose proposed a more nuanced view. They realized that photons, particles of light, from different parts of a three-dimensional object take different amounts of time to reach an observer. For example, light from the far side of a fast-moving cube would take longer to reach a camera than light from its near side. When a camera takes what seems like an instantaneous snapshot, it's actually collecting photons emitted at different times. This time difference effectively stretches the image, which surprisingly counteracts the expected length contraction, so the object doesn't appear to change length. But there's more. For this cancellation to happen, light from the object's leading edge must have been emitted later than light from its trailing edge. Because the object is moving during this light travel time, normally hidden parts of the object become visible. The overall effect, as Tyrrell and Penrose showed, is that a 3D object moving at nearly light speed will appear rotated. For decades, verifying this was impossible because we can't accelerate everyday objects to such extreme speeds. But recently, physicists in Austria devised a brilliant solution. At the Technical University of Vienna and the University of Vienna, they used pulsed laser light on a stationary sphere or cube. These laser pulses were synchronized with an extremely fast camera, a picosecond camera, collecting the scattered light. By compiling images recorded from different laser pulses, they effectively reduced the perceived speed of light to less than 2 meters per second. Under these slow light conditions, they observed that the objects indeed appeared to rotate, not contract, just as predicted. There were some minor deviations from theoretical predictions, but these were attributed to simplifying assumptions in the theory, like assuming incoming light rays are perfectly parallel, which only happens at an infinite distance. This experimental breakthrough provides tangible evidence for a long-standing theoretical prediction of special relativity. The technique of using ultra-short laser pulses and high-speed photography to simulate relativistic conditions opens new avenues for visualizing Einstein's often counterintuitive theories. Interestingly, this research also stemmed from an art-science project focused on ultra-fast photography and the concept of slow light. It's a wonderful confirmation of fundamental physics and a showcase for innovative experimental design.